Okay, so remember what we finished up with last time was not that interesting. It was just notation, right? We said that if we have a matrix A, then we use something like this to denote the ith. This denotes the ith column of the matrix A, and this denotes the jth row of A. And so we could abbreviate A in two ways. We could either write it as a bunch of columns, right? A bunch of columns, or we could also write it as a bunch of rows. Okay, right. A bunch of columns or a bunch of rows. Okay. And the reason we're doing this, this notation is going to be really handy. First off, we're going to use it to describe matrix multiplication. Matrix multiplication. Okay. Matrix multiplication. And you remember how we defined matrix equality. Matrix equality just meant that everything was equal entry by entry, right? Then matrix addition was you just added everything entry by entry. And so, if you're naive, you might think, well, matrix multiplication, maybe it's going to be just multiplying entry by entry. Okay, that's maybe that would be one way to do it. That's not maybe the most. That's not the most. That's not the best way to do it. What turns out to be the best way is something related to the dot product. Okay, so does everybody know what the dot product is? Anybody not know what the dot product is? Okay, that's all right. Okay, so dot product of vectors. So if you have one vector u. Okay, so we haven't even talked about vectors, but if you have a bunch of numbers, an n tuple of numbers, say a1, a2, a3, an, and you have another bunch of numbers b1, b2, b3, bn, then these n tuples, an n tuple of real numbers, n tuple of real numbers. So also called a vector, right? A vector. Then there's a way of defining multiplication on it called the dot product. So let's call this vector A, vector B. We define the dot product A dot B as a number. Okay, the dot product of these vectors is going to be a number. That number is A1 B1 plus A2 B2 plus A3 B3 plus AN BN. Okay, so you just multiply. You multiply the corresponding entries. You get that product. You get n products, and then you add them all together. Okay, and that's called the dot product. Okay, so so for example, right, if I have 1, 2, 3 dotted against 0, 2, 1, well, that's going to be 1 times 0, 1 times 0, plus 2 times 2, plus 3 times 1, right? In other words, 7. Okay, so the dot product of these two vectors is 7. Okay. Let me also write here, because I hope you know it already, the sigma notation. So I can abbreviate the sum. Instead of writing the sum out, I'm going to write it. You can abbreviate this as summation ai bi as I goes from 1 to n. I hope everybody, has anybody not seen that? Anybody not seen that? The summation notation? Everybody okay with that? Okay, so summation notation, right? This is the sum of AI BI as I ranges from 1 to n. Right? That's how you read that in English. Okay? Okay, so the dot product. Okay? Okay, so we're talking about matrices and matrix, how to do arithmetic with matrices, and we want to talk about matrix multiplication. The best way turns out to be the following. So the best way turns out to be the following. Okay, so here's the definition. So I'll put up the definition first, and it'll seem kind of abstract, and then I'll do a concrete example, and that will bring it down to earth. Maybe I should do it in the opposite way, but I'm going to do it in this way, just so that you can stretch your brains a little bit. Okay, so given A, which will be an n by n matrix, where, of course, I ranges from 1 to m, k ranges from 1 to n. Given A, one matrix, and B, kj, where k, n by s matrix, where k ranges from 1 to n, and of course j from 1 to s. The matrix, the product, AB, is defined to be the m by s matrix. M by s matrix, Cij, where the ijth entry of the new matrix is the dot product of the ith row of A against the jth column of B. Okay. So remember, this is the ith row of A. This is the jth column of B. Okay, so so just to remind you, this A sub I dot bj is going to be the dot product of the ith row of A, right? The ith row of A, so that's going to be A I1, A I2, A I n, n columns, dotted against the jth row of B. Okay. Just for practice, I want you to write down what I'm going to write here. Okay. How do you describe the jth row of B? Just so you get familiar with the notation. Just write it down. Yeah. Take 30 seconds, write it down. Okay, turn to somebody nearby and say, this is what I wrote down. Make a new friend. Or an old friend. Later on we'll play a friend making game. Okay, so, Reed, you were first. What do I write here?
BJ, or bold B, J1. Bold.
Is it a bold B? Actually, the bold B. So
that's the row. Sorry,
yes,
just BJ1,
yeah,
BJ2, BJN.
Exactly. BJ1, BJ2, BJ. BJ what? What's the last one? BJ N. BJ N. Yeah. So yeah, so here the entries are not bolded. The entries are not bolded because they're numbers, right? If it's bolded, it's some sort of vector, right? Okay. So yeah. So right. So
those were bolded, but it described the whole matrix B.
Oh, wait a second. So is this right? Actually, this is not right. Right? Because this is, the first one describes the row and the second one the column. Right? So what you've got here is the jth row, first column, jth row, second column. Right? So it's not J1, but actually, it'd actually be 1J. Right? 1J. Right? Because you want the jth column, you don't want the jth row. Right? You're not dotting the ith row against the jth row. You're dotting the ith row against the jth column. 1J, 2J, NJ. Okay. Yes, Sam?
Can you explain again why it's not a vector?
Why? What's not a vector?
Like why we don't put the symbol?
Oh, because these things are numbers, right? We're dotting the ith row against the jth column, right? This is the ith row. This is the ith row of the A matrix, right? Each of these things is a number, right? It's not that each of these things is a vector, right? You don't have a vector where the entries are vectors also. That would be interesting. Right? That would be a matrix actually, right? Yeah. So we're just taking you have some matrix, 1, 2, 3, 4, 5, 6, and you're dotting it against some other matrix, 3, 4, 5, 6, 7, 8. Right? Oops. Yeah. Okay. Right, so these guys, if you're taking the second row, well, each of the entries is a number, right? Each of the entries is a number, column, each of the entries is a number. So, yeah, so right here, right, B is the matrix where B sub kj are the entries. Okay, these guys are the entries. Yeah, Lizzie.
This might be a silly question, but is there any significance to both matrix A and matrix B having n in them?
Well, so you notice that if they didn't have n, then you'd have a vector of one length, and then you have a vector of a different length, and you wouldn't be able to take the dot product. So it wouldn't make any sense. Okay. So we actually do need. You're sharp in noticing. Or you've noticed that this and this have to be the same, or this and this are the same. Why do they have to be the same? Well, because we need to take the dot product of the rows here against the columns here. So the length of the row must equal the height of the column, right? The length of the row in the first guy must be the height of the column in the second guy. In other words, we can't multiply. If this guy were. So right now this is 2 by 3, and this is a 3. Let me change it to a 3 by 3. So 7, 2, 5, say. Okay. So it's okay to multiply them in this order, right? We would get a 2 by 3 out of this, right? But if we switch the order, it wouldn't be okay to multiply them.
Yeah. So you can't take B times A.
That's right. That's right. So B times A is not even defined.
Okay.
Okay. So it's even worse than the commutative law failing. It doesn't even make sense, right? So it might not make any sense. Okay. So yeah, but yeah. So I'll say that again in a second. But let me just go back to here. Okay. So right. So in sigma notation, this is summation aik bkj as k ranges from 1 to n. Right? So summation aik, bkj, right? You take ai1 times b1j plus a12 times b2j, et cetera, right? So this is what you get. So this is the ith ijth entry of the product. Okay. So let me, like I said, let's just bring this down to earth. If I have some matrix, some product of matrices, right? So the way you calculate it is say, okay, well, this is a 2 by 3, this is a 3 by 3, so I know this is going to be a 2 by 3, right? This is going to be a 2 by 3 matrix, right? And you say, okay, if I want the 1, 1 entry, right? If I want C1, 1, right? C1, 1, well, I need to take the dot product of the first row against the first column, right? So I get -3 plus 4 plus 0, right? So that's 1, right? The dot product of the first row against the first column, right? Okay, take 5 seconds and tell me what this is, or tell the person next to you what this is. Okay, tell the person next to you. What is it? What's this number? What should go here? Anybody want to say? Read.
Second row, first column.
Yes, yes. So second row dotted against the first column, and so what do you get?
Oh, 1.
1, exactly. Right. So right, this is C2, 1. Right. So you take the second row against the first column, dot product of the second row against the first column, so you get 1 plus 0 plus 0. Right. In other words, 1. Okay. Okay. Do we need to do more of this, or that's you should be okay? I hope you're okay. Okay, good. Okay, so right, to get this number, you would say, okay, I'm taking the first row. This is C1, 2, right? So you take the first row against the second column, right? You get -1, -6, 5, 2. Okay, so you get these numbers by taking the dot product of the appropriate row against the appropriate column, right? So Cij. So remember, again, Cij is just the AI dotted against Bj. Okay, and as Lizzie noted before, even if AB makes sense, BA may not, right? So you could multiply one way, but maybe you can't multiply. If you switch them, it doesn't make any sense to multiply. Okay, and it's even worse than that. Even if BA exists, it still might not equal AB. Okay, so matrix multiplication is different from numerical multiplication, right? It's not commutative. Okay, so you don't have, there's no commutative property, for matrix multiplication. Okay. Okay. Let me make one observation that's going to be really important. So, key observation. Okay. So notice that if I take -3, 2, 4, 1, 0, 4, and multiply it by 1, 2, 0, what do I get? What do I get? Right, so I'm just taking this guy against the first column of the second matrix. What do I get? Yo.
So you get like 1 and 2 matrix 2 by 1.
You get a, so this is a 2 by 3, and this is a 3 by 1, and so you get a 2 by 1, right? And what 2 by 1 is it?
1 and 2.
1 and I hope 1. Right, 1 and 1. Yeah, 1 and 1. That's okay. Okay, so you just get the first, of course you get the first part of the matrix that we calculated already, right? Okay. And if I multiply this matrix by the second column, 1, negative 1, 1, well, I'm going to get the, the second column of this matrix, right? And I do the third column, I'm going to get the third. If I do it against the third column, here I'm going to get the third column of the matrix. Okay. So what I'm saying is that the general principle is that AB is going to be a matrix consisting of A against A times the first column, A times the second column, A times the first column of B, A times the second column of B, etc., A down to D, A times the S column of B. Okay, now that seems like a trivial observation, and it is actually, but it's going to be really, we'll use it a lot. We'll use it a lot. Okay, so matrix multiplication from the left occurs column-wise, right? Maybe that's how you want to remember this. Matrix multiplication on the left occurs column-wise. Okay.
What do you mean by on the left?
I mean, you've got this B, and you're multiplying by a matrix on the left.
Oh, okay.
Okay. You've got B, you're multiplying on the left. Well, you might as well multiply each of the columns of B by A individually. It's the same thing. Okay, another thing I should say is that when mathematicians say, in normal English, when you say in general, it usually means like there's some exception. But when mathematicians say in general, it actually means like in the general case. So like the general principle is, or something like that. So it's actually completely different from how you say it in what people say in English. So watch out. If I say in general, I don't mean that in general it's like this, but there's some exception. I mean this is always like this. Okay, so it's not like in general the students are hardworking, right? It's not like that statement, right? Right. If a mathematician says in general the students are hardworking, that means that they're all hardworking. Yeah. In the general abstract case, basically. Okay. So we now have matrix multiplication, and one thing we can do with it is to use it to simplify linear systems. Relation with linear systems. Relation with linear systems. Okay, so it turns out that this gives us a nice way of expressing linear systems. It's not particularly exciting, but so suppose we're back at the beginning and we have an m by n system. The system looks like a11x1 plus a12x2 plus a1nxn equals b1, a21x1 plus a22x2 plus a2nxn equals b2, am1x1 plus am2x2 plus amnxn equals bm. Okay, suppose you have this system that has m, there are m equations and there are n unknowns. We can abbreviate this system by taking we can abbreviate the system as follows. Let A be the matrix Aij, where I ranges from 1 to m, j from 1 to n. Okay. Let the vector x be x1 through xn. Okay. And let the vector b, the column vector b, be the constants b1 through bn. Okay. What does AX equal B mean? What does AX equal B mean? Well, that would mean that the matrix A11, A12, A1n, AM1, AM2, AMN, X1, XN equals B1, BN, BM. Excuse me. This is the same thing as saying this. Right? AX equals B. Right? This is an m by n. This is an n by 1. This is an n by 1. Okay. Well, what does that mean? Matrix multiplication. On the left-hand side, we should get an m by 1. On the right-hand side, we have an m by 1, right? B1 through Bm equals some sort of m by 1, right? What's the first entry of my m by 1 matrix? Take half a minute, take 30 seconds, and write down the first entry of the product, the top entry of the product. Okay, turn to somebody next to you or around you and say, this is what it is.
I just get really mixed up with like the I's and J's and everything.
Oh, because it's the
Okay, would somebody like to tell me what the first entry is here? Anybody? Or do I have to choose somebody at random? Yes, Lizzie.
Is it A11X1?
No. You're close. I mean, you're sort of, Molly?
Well, I'm not sure if this is right, but I expressed it as a summation of A1IXJ.
Yeah. What are I and J?
So ranging from 1 to n for I, and ranging from 1 to I guess.
Okay, so yeah, so they should actually be the same. You don't
Okay,
want to
so
use I and J, you want to use
both
I and
I.
I.
Okay.
Yeah, they should both be I's. Yeah, good. So so remember what matrix multiplication says, right? It says the thing here should be the first row against the first column, right? This is the 1, 1 place, so it should be the first row against the first column. So it's going to be A1, 1, x1 plus A1, 2, x2 plus ... plus A1 and xn. Right? Okay. Okay, so that whole sum is your first entry. Okay, the dot product of the first row against the first column is your first entry, right? And then the second row is going to be the second entry is going to be the second row against the first column, right? So you're going to get A21 x1 plus A22 x2 plus A2n. Let me move this over. Running out of space here. A2n xn am1 x1 plus am2 x2 plus amn xn. Right? Okay. Okay. Everybody all right? Any questions? Anybody lost? Okay. So what does AX equal B mean? Do you have a question?
Is that just the same as what up there?
It's the same thing as this, exactly. Yeah, it's the same thing as this. Yeah, so that's the answer to what I just asked. What does AX equal B mean? It means that this matrix and this matrix are the same, right? In other words, this equals B2, blah, 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 this equals Bm. In other words, the system, it's the same thing as saying that the system is true. Okay, so this thing can be abbreviated as AX equals B. Okay, where A is this matrix, X is this vector, and B is that vector. Okay, so you have a handy way of expressing the system of linear equations. It's AX equals B. Okay, just like you've returned to junior high school, right? AX equals B. Okay, it's just that everything is different right? This is a matrix, this is a vector, this is a vector. Okay, so it's a handy shorthand. Okay, so it turns out that the question we were talking about from the very beginning is actually this question, right? Can we solve AX equals B? Okay. Okay, so you like I said, you've gone back to junior high school, right? You're back solving this sort of question, right? AX equals B. What is X? Right? What is X? Of course, in junior high school, you just divide by A, right? So you're hoping, right? Now you're in college, you're hoping we can just divide by A somehow, right? That turns out not to be possible. Okay, but sometimes something like it is possible. Okay, so we'll talk about it. Okay, we'll get to that. Okay, so not so simple as just dividing by A, because what does it mean to divide by A, right? What does it mean to divide by a matrix? Can you always? It turns out that it's sometimes possible to, but it's not always possible. Just like back here, right? If you had 0x is equal to 5, right? You couldn't just say, oh yeah, I'm going to divide by 0, right? Sometimes you weren't able to divide by the coefficient, right? Sometimes you can, and sometimes you can't. Okay. Any questions? Any questions? Yes?
So under that matrix, the one that's the same as the n by n system,
Yes.
is that written as n, that matrix is m by 1?
M by 1, and this is also an m by 1,
Okay.
right? Because this was an m by n times an n by 1. So this is actually just a column vector.
Mhm.
This is also a column vector.
Okay.
And to say that they're equal to each other means that this equals this. In other words, this right? The second one equals this. In other words, the second one is satisfied, etc., etc. Okay, so yeah, these are single entries all the way down. Okay, other questions? Okay. Another key observation that seems not interesting but will be quite useful. Another key observation. Notice that this AX that we had over here, we could also write that as x1, right? This thing is AX, right? This guy here is AX. This AX here could also be expressed as x1 times the first column of A, x1 times the first column of A, plus x2 times the second column of A, plus xn times the nth column of A. Right? It's x1 times the first column, a11, a21, m1, plus x2 times the second column, a12 down to am2, plus xn times the nth column, a1n, amn. Okay. Okay. Is that clear? Is that clear? Everybody see that? Right? This thing here is the same thing as x1 times the first column plus x2 times the second column plus the xi times the corresponding columns. Okay, so asking, is there a vector x satisfying ax equals b is the same question as can you find numbers? Can you find coefficients x1 through xn such that x1 a1 plus x2 a2 plus xn an equals b? Okay, let me make that concrete. So suppose A is 1, 2, 1, negative 2, and B is 4, 0. Okay. Can you find? Looks like people are still looking. Let me hold on. Let me wait for a minute. People are catching up. Okay, so everybody look here. Okay. Here's a matrix 1, 2, 1, negative 2. Here's a vector 4, 0. Can you find coefficients x1 and x2 so that x1 times the first guy plus x2 times the second column equals 4, 0? Can you realize 4, 0 as some sort of combination of the columns here? Anybody just see it immediately? What should we take? What coefficients should we take to get 4, 0? What? 2 and 1. Yeah, that'll do. Right, 2 and 1. So yeah, yes. Can we solve this? Right? Yes. Take x1 to be 2 and x2 to be 1. Right? Okay. And then you see that 1, 2, 1, negative 2 times 2, 1 is, well, you get 2 plus 2 is 4. 2 plus negative 2 is 0. Right? So 2, 1 is the solution, right? 2, 1 is the solution to ax equals b. Okay. So solving ax equals b is the same thing as answering, can I find combinations of the columns that give me b? Okay. Can I realize b as a combination of the columns of a? Right? Can I realize b as a combination of the columns of a? Okay. We need to introduce a definition, because if I say combination, that could mean anything. So there's actually a specific term. It's called a linear combination. That's a linear combination. So let's define. Let me put that down. Let v1 through vn be vectors in Rm. Say any sum c1 v1 plus c2 v2 plus cn vn, where the ci are all real numbers, is called a linear combination. Linear combination of the VIs, V1 to Vn. Okay, and what we've just observed is that the question, can I solve ax equals b, is the same question as, can I realize b as a linear combination of the columns of A? So that's the observation. Okay, so for example, if I let C be -3, -2, and I say, can you solve AX equals C?
Oh, say
With the same A? Yeah. With the same A? Maybe try that. Can you realize -3, -2 as a combination of the columns? Try it for 1 minute and see if you can get an answer. Actually, this one's a little bit. Maybe I'll leave this to the homework. It may take you. It's not as immediately obvious as this one. But did anyone get it? You don't get it? Ross, yeah. Tell me what it is.
It's the -5 and -1/4.
-5 and -1/4. Is that right?
Isn't it -5 halves?
Yeah, I think it's -5 halves. Yeah, -5 halves. Yeah. 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 It turns out to be -5 halves and x to being -1/4. Right. Okay. So yeah. So this one turns out to be, if you take -5 halves times the first one and -1/4 times the second, then you get, I'm sorry, you get this -3 over -. Okay. Okay. Sorry. That was longer than I thought. Okay, so let me just say one last thing, one last definition related to this. The set of all linear combinations of some vectors v1 to vn is called the span of v1 through vn. It's called the span of those vectors. Called the span of those vectors. Okay, so geometrically, like if you're in space and you have one vector and you have another vector, two vectors in space, and you look at their span, well, that's going to be all linear combinations of these guys, right? So you say, okay, I take this vector and I add on the other vector. I take twice this vector and I add on the other vector, right? Do you see what you get? You're going to get the plane containing those two vectors, right? The plane described by those two vectors is the span. Okay. Okay. So there's some geometric meaning to the span. Okay. And so we can rephrase this question just one last time, saying that the question is the same thing as asking, is B in the span of the column vectors of A? Right? That's just exactly the same thing, right? Is B a linear combination of the columns? In other words, is B in the span of the columns? Okay, that's it for today.